Okay, this is the last class meeting of the Introduction to Optimization. We have two announcements related to the homework 7 and final exam. Both are due on next Wednesday. Let me start with this Venn diagram, which is one of the most important Venn diagrams I have shown you in this course. This universal set is the set of all constrained optimization problems. And there are two, actually around 5, important subsets of this set of all constrained optimization problems. First one is this one, the constrained optimization problem with functional constraints. Here, functional constraints means that our constraint set omega can be written in this form. So by introducing inequality constraint functions and equality constraint functions, our explicit constraint can be described. Of course, our constraint set is the intersection of the domains of these functions and this explicit constraint set. And another big one is the set of all convex optimization problems, where we have a convex objective function which is defined on the constraint set omega, which is also convex. So I just told you that the general convex optimization problem has a convex objective function defined on the convex constraint set. Now, what is the intersection of these two? Definitely it's a convex optimization problem with inequality and equality constraints. So as described here, it looks like the same as this one. The difference is that anyway, the constraint set omega, which is the intersection of the explicit constraint set and the domains of these functions, must be a convex set. Okay? And among them, there is a smaller subset in this form where this f underscore is a convex function. So the component functions are convex functions of x. And here h is ax minus b. That is affine. Okay? So when our convex optimization problem is formulated in this form with convex inequality constraint function and affine equality constraint function with convex objective function, it is called standard convex optimization problem, and it is fully investigated in Stephen Boyd and Vandenberg's textbook. And as I told you, there is a lecture available on YouTube. Textbook is available on the web, and lecture note is also available on the web, so you can study yourself. Got it? And a subset of this standard convex optimization problem is our linear optimization problem. So here we had what? So for this one, we had minimization of C transpose X subject to we have AX equals B and X greater than or equal to 0. Of course, we can have other constraints, but as we've seen, any linear programming problem can be put in this standard form. So as you compare with this one, see that this is linear, which is a special convex function. So here, and we have AX equals B, AX equals B, minus X less than or equal to 0 is here. Got it? So the big picture looks like this. Of course, there is a bigger set, including this set of all constrained optimization problems and its complement, the set of all unconstrained optimization problems. And we've learned a lot of things. So given that, last time I just skipped that this convex optimization part, but I've changed my mind. So let me quickly read through this note for chapter 21. Okay, So this is our general constraint optimization problem. And we may ask some questions. This is the first question. We've seen some first necessary conditions for a feasible solution to be a local minimizer, right? This question is that when an F1NC, F1SC necessary condition is sufficient for global optimality. Be careful. Those F1NC's first order necessary conditions were stated in this form, usually. If X star is a local minimizer, got it? Local minimizer, then some condition is satisfied. But here, it's not talking about the converse. The converse would be if such conditions are satisfied, then X star is a local minimizer. We are not talking about that. We are talking about more stronger one, global optimality. So there should be a very special subset of constraint optimization problems, right? So given this set, there would be a very special subset where first order necessary conditions for local optimality implies global optimality. And interestingly, this set is contained in that set. Okay? I'm not saying that this is the if and only if condition. I'm saying that this is a sufficient condition for local optimality implies global optimality. Got it? So this may be too special, but it's worth to investigate. So that's why people developed a new theory. Let's recall some first order necessary conditions. We learned some of them too long ago in the early of this semester. Something like this. Okay? So here, whenever I talk about first order necessary conditions, what? You have to remind that, okay, the involved functions are C1 functions, continuously differentiable, right? So given continuous differentiability, but then obviously we want to involve our theorem with the gradient of the objective function. So here, as you see, gradient of objective function appears. And of course, in this tubulets, you don't see, but actually Lagrange condition is what? Gradient at X star is a linear combination of what? The gradient of equality constraint functions. Here, what is the Kkt conditions? The gradient of the objective function evaluated at star is a linear combination of gradient of equality constraint functions and gradient of inequality constraint functions. So all of them involves the gradient, first order derivative of our objective function. Now, some of you still remember, I believe, that I've given you why this is not a sufficient condition. If you think simply, naively, then it seems this is a necessary and sufficient condition. It's like you look around every here, so suppose you are here. And you look at every possible direction with infinitesimally small displacement. And then what? Some of them may be feasible and some of them may not, right? So from here, these directions would be feasible directions. Then it seems that apparently gradient of f of x star inner producted with any feasible direction is greater than or equal to 0 means wrongfully means local optimality. But it is not. And I've given you an example. What was that? First, I introduced a very weird looking constraint set. So something like this. You use circles to construct this constraint set omega. And I introduced an objective function that is quadratic, but having one positive eigenvalue and one negative eigenvalue. So that this point is a saddle point. But along this direction, you have a quadratic function that achieves minimum here. But along this direction, you have a negative quadratic, so that, for example, the point here may be smaller than this one. Okay, got it? And something like that. So definitely here at x star, what is the only feasible direction? This direction. This is the only feasible direction, because here it looks like this. Okay, but if you magnify this area, you will see what? Whatever small area you find, there exists some point here with very small distance to the origin, where the function value is smaller. So this point origin is never a local minimizer, but this condition holds there. Got it? So this is important. This example is worth to remember. Okay? And you may see in the final exam, okay? Because I emphasized in the last lecture, last meeting. Anyway, let me go back to the lecture note. So this is a necessary condition. Never forget that. But if x star is an interior point, which means that if you find a very small ball around x star, every point inside the ball is feasible. In that case, by extending this one, you can get that. Okay, it's simple. You just, since every direction is feasible, first you move to the first direction to the that corresponds to the first basis vector 1 0 0 0. Then that must give you that, and you do what? You move to the negative of that. Okay, and now you move to the second basis vector 0 1 0 0 and negative direction, and then you will see this is 2. It's very simple. You just put them together, then what you have, that identity matrix times gradient is greater than or equal to 0 and less than or equal to 0, so equals 0. What does that mean? Since the identity matrix is invertible, gradient is 0, something like that. So actually this implies that one. Now for these two, we studied in some of our recent lectures, right? So you remember what is the Lagrange conditions when we have only equality functional constraint, and what is the Kkt conditions when we have equality and inequality functional constraints. Now the note shows the definition of convexity related to set, and then convexity related to function. As I told you, a convex optimization problem has a convex objective function defined of convex constraint set. So even though I say convex, one convex, that word is for a function, and the other convex is for a set. We start by defining a convex set. So here, a set is convex if for any feasible, in terms of our objective function, okay, any feasible point solution, the line segment, so we start from y and move to z, line segment is contained in the constraint set. Got it? But this can be interpreted in an interesting way. Since most of us are communications major, we can say that every point is visible from any other point. Visible means that we can draw a straight line, right? So you may say that every point is on line of sight. Okay? Line of sight means that you can see it. Got it? So convex set omega means line of sight. So let's check whether this set is convex or not. Is this a convex set? No, because if you want to see this, you must draw a straight line, and this straight line is not inside the set, constraint set. Got it? So the reason why this special case does not allow this FONC become FOSC is one of the reasons is that this is not a convex set. Got it? Then let's see some examples that are very simple. So line of sight condition is satisfied, right? Among any point. Here, again true. Here, this is a half line, again true, right? On the contrary, as you see, this is kind of non-line of sight. Non-line of sight. So they are, these two sets are not convex. Got it? So very simple. Remember this line of sight interpretation. Then your intuition may work quite well. Got it? Now, here goes some examples of convex sets. Empty set is convex, interestingly, but it's just due to some logic when we define. So ignore it. Anyway, if the set is empty, what? No solution exists. No feasible solution exists so that we have no solution. A set consisting of a single point. Well, convex. By the way, what about you have finite number of points in the Euclidean space? Is that a convex set? No. Because if you have this point and that point contained in the set, line segment definitely is not contained in the set. Okay? Line or line segment itself is a convex set. A subspace, what is a subspace? Subspace is described by a matrix times vector equals 0 type, AX equals 0 type thing, right? That is a subspace, and you know that satisfies line of sight condition. Hyperplane, what is a hyperplane? A transpose X equals B, right? So you have a normal vector, and now this may not contain the origin. But anyway, this is a special case of linear variety. By the way, linear variety is simply put AX equals B. Okay? So actually, this includes that and that. Half space means that it's similar to half plane. So A transpose X equals B is a hyperplane. Half space means that A transpose X is greater than or equal to B type thing, or greater than B. In that case, half of the entire Euclidean space is the set. Of course, the entire Euclidean n-dimensional space is convex. Another interesting thing is that this condition, we've seen a lot of times, right? Positive non-negativity constraint. We've seen it in the standard linear optimization. And also, I've given you some interesting example when we study the Kkt condition. We specialize the condition so that we removed any equality constraint and just to put inequality constraint like that. And in that case, our complementary slackness combined with the first order thing reduced to what? Gradient of F evaluated at X star transpose what? X equals 0, orthogonal. You remember that? At the boundary, this vector and that gradient is orthogonal, something like that. Okay, so this is very special but an interesting constraint. And this is convex. And you may say that, well, it's obvious. Kind of, right? In two-dimensional case, it's the first quadrant and every point, 2 points are line of sight. Okay, so anyways, the proof is just for preciseness. As far as you have that intuition of line of sight interpretation, then it's piece of cake. Now, this is so-called linear variety. You may say that. It's a special case, actually. You may put inequality, but anyway, this is convex, and you can show that. Now, here goes the definition of convexity of a function. By the way, it starts like this. You are given a convex set. that is the domain of this function we are talking about. So as I told you last time, a convex function defined on a convex set that contains the redundancy. I have to say, precisely speaking and concisely, a convex set, a convex function on a set. In that case, that set must be convex. Okay. As far as I'm talking about convex function, there is a domain, and domain must be convex. But anyway, so here we consider the domain a convex set, and the function's convexity is defined this way. When I first saw this, I said, "What the HELL?" But you don't need to be frustrated. Let's simplify. Okay. So we consider a function of scalar like this. Okay. And let's try to understand. So whenever probably your lessons attained in your multivariate calculus and linear algebra is that whenever you have some abstract result, you visualize that in 1, 2, or 3-dimensional space, right? So we do the same thing. So even though that definition of convexity assumes this argument can be any convex set, this omega is not necessarily a subset of n-dimensional Euclidean space. It may be any arbitrary complete normed vector space, actually. Okay? I will talk about that later today. Got it? Anyway, but if this is a general definition for any case, this definition must be applicable to the simplest case. So we consider, okay, a function of a scalar. So let's say that this is point x and this is point y, and this is our function to be claimed as a convex function. Now, let's see the argument. What is that? Why this figure does not match with that? Here we have x and y. Okay, so just change this to x. Got it? Now, the argument depends on alpha, but as you know, when the alpha is only between 0 and 1. So by changing alpha, you move from here to here or here to there. Okay? So it's a kind of how to say it? Intersection. Yeah. Anyway, something some point that divides inside. Okay. So if you evaluate that point, this is the function value, f of ax plus 1 minus ay, right? Now, what is this one? First, f of y is this value, this value, right? Now, what is, let's say, f of x? What is f of x? This value. Now, you mix this one by weighting alpha and weighting 1 minus alpha. And you move. So you move here. Now, for better understanding, let's connect these 2 points. X comma f of x and y comma f of y. Then, what does this mean? What does this mean? This means that this line segment is always above this curve, right? See that? This is the curve and this is the line segment. Okay, so this is convexity. Got it? Yeah. As we will see, another interesting thing is this. If a function is convex, any linear approximation, first order approximation, so in this case, this straight line at x, right? Got it? Then the entire function is above this supporting plane. Precisely speaking, supporting hyperplane. See that? Am I right? So you view a function in one higher dimension. That is graph, right? Right? This is a graph. This is a graph of the objective function. Be careful. And then in this one-dimensional higher space, you draw a hyperplane, supporting hyperplane. Then the function is always above the of course, above and equal to the supporting hyperplane. That is one important property of the convex function. Now, you may say that, are we done? Yes, very simple. The convex set is a very simple set. Convex function is very simply defined. Now, we say that, okay, let me formulate an optimization problem with a convex set on a convex constraint set. A convex function, minimization of a convex function subject to convex constraint set. That is general convex optimization problem. And given general convex optimization problem, we may prove a very interesting property. So I little bit hate the ordering of the results presented in textbook. So let me give you my reasoning. Okay. So first one is that the important properties of convex optimization problems. So the first one is this. A local minimizer is a global minimizer. See that I'm talking about general convex optimization problem. I'm not talking about standard convex optimization problem with functional constraints. I'm just talking about a convex objective function defined on a convex set and claim this is true. By the way, is the converse true? Well, of course, by definition, right? Global minimizer is always local. So this means that in general convex optimization problem, global minimality is local minimality means global minimality. Oh, by the way, how can you prove this? It's not difficult. You use proof by contradiction. So you start saying that, okay, X star is a local minimizer. Okay. Suppose that this is not a global minimizer. Because our theorem itself assumes the existence of global minimizer, we may say that star, okay, that they are both stars, but anyway, let me use this star and that star, okay? And what can you say? This means that f of x star is greater than f of x this star. Am I right? Because this is global and this is not global. Means that this cannot have the same value as this one. Am I right? Got it? So this assumption means that one. Now what do you use? You use the definition of the convex set and definition of the convex function. So what you do is that, for example, if I visualize that, suppose this is x star and that is x star, and you have function like that. Let me go back. Yeah. Right? Maybe not differentiable, right? So I'm not assuming any differentiability. So let me do this. Got it? So this is f. So locally this is a local minimizer and this is also a local minimizer. Now what do I do? I consider a line segment connecting these 2 points, which translates to a line segment connecting these two, right? Now what happens? This line segment must be above this function, which means that if you move that direction, function value must decrease. That means this is not a local minimizer. Done. Got it? Very simple. Okay? So it's a very simple proof. Anyway, sketch of the proof. So this holds for general convex optimization problem. Very, very powerful. Okay? So you remember, right? It holds here for every convex problem. This is true. Now you have some other proofs. But before we do that, let me emphasize this. From the second properties, they all assume the objective function is continuously differentiable, which means that we are going to involve the gradient. Got it? Okay. So let's see. This is what I just told you. This curve is a graph. You know what is a graph given a function? Okay, let me remind you, because some of you may have forgotten the definition. Function and its graph. By the way, this graph is nothing to do with the graph theoretic graph. Okay? This graph is related to visualization of a function. Suppose you have a function something like this. Okay? Just for simplicity, you may define a smaller set. To R. Okay. Then what is a graph? Graph is a set of points. By the way, what is this point? What is the length of this pair? This is length n. This is length 1. So Rn plus 1. Got it? Such that no, I'd better say this. Y in Rn where I'd better say this. Okay. So this is the graph. Of course, we need, Got it? So a graph is a set of points, n plus 1. Set of points. One dimension higher than the original function's dimension. Got it? So in the special case where n equals 1, then what is a graph? So here you have R and this, right? This is the set of points. When n equals 1, set of length 2 points, right? Some x comma fx. Got it? So this is a graph. Now let's increase the dimension to 2. No, in this case still 1. Now this is the graph of our convex function, and this is called epigraph. This area, okay, this set of points is called epigraph. What does that mean? The points in R to the n plus 1 that is greater than the graph. Okay, this is called epigraph of function. And as I just told you, wherever you find the supporting hyperplane, then this epigraph is above this hyperplane. Okay, that is, you can show that it's a if and only if condition for this function to be a convex function. Okay, so convexity of a function can be rephrased. Okay, now even though we do not talk, but when the function is twice continuously differentiable, there are other sufficient conditions for the function to be convex. That is this one. Okay, if Hessian matrix is always greater than or equal to 0 on the convex domain, then it's a convex function. You know this from your high school math, actually. Anyway, for the quadratic if the eigenvalues are all non-negative, it's a convex function. So, as I told you, general convex optimization problem is stated like this. Here, this is a convex set. Actually, this intersected with the domain of F. But anyway, convex function defined on the convex constraint set. Sometimes we call this a convex programming problem or convex optimization problem. And linear programming, as I told you already, is a special convex optimization problem. By the way, here, what is this QP? Quadratic programming. But here, the quadratic function used as the objective function must have what? Non-negative eigenvalues. Otherwise, the function is not a convex function. And then your set must be a convex set. Now, as I told you, in convex optimization problem, global minimizer if and only if local minimizer. And the proof only utilizes the definition of convex function and definition of convex set. Now, here we start to use functional constraints. So suppose that our, for example, our inequality constraint function looks like this, where G is a convex function. Then what? Interestingly, this set is a convex set. Such a set is called sub-level set, because if it is equal, then we call this a level set of function G at level C. Sub-level means that level is less than or equal to this some constant. So sub-level set is a convex set. That's why in our standard, see that? In our standard convex optimization problem, what do we have? This inequality constraint function is a convex function. Then this sub-level set becomes convex. Precisely speaking, each component function gives us a convex set. And you can easily show that intersections of convex sets is a convex set. It's kind of obvious. You have a line of sight area, and you have another line of sight area, and you consider intersected area, they must hold line of sight property, right? So that's why this convex inequality constraint function is so important. Anyway, now, as I told you, we see more properties assuming the one-time continuous differentiability of our objective function. And in this case, the equality and inequality constraint functions. Okay. And then the first order necessary conditions are all first order sufficient conditions, not just for local optimality, global optimality. Actually, these are for what? A local property. But I've already told you that in convex optimization problem, local property is global property. Got it? This is very interesting. I'm not talking about some numerical approaches, but since this convex optimization problems have this very nice property, just some algorithms constrained or unconstrained problems for if you have an algorithm and if you just move down here, sometimes it's just guaranteed that you reach the global optimality. But be careful. Suppose you are in some very high mountain like Mount Everest and you go down. Is it guaranteed that you reach to the village in the sea level? No. You may just move 1/3, 1/9, 1/27. In that case, you may never reach the sea level, right? So be careful. Moving downwards does not guarantee. But in order to reach the global minimizer, you must move downward. Okay, anyway, be careful. Anyway, so we want to prove these things for first for convex optimization problem. Since I don't have enough time, I'm not going to talk everything. But these are all what we studied throughout this entire semester. And interestingly, in this convex optimization problems, this is sufficient for local optimality. Means global optimality. So wonderful. Got it? Let's see some proofs like this. Okay. So if this holds, the first one, this holds, then it's a global minimum. How can you prove? Since we assume one-time continuous differentiability, we may use that property that supporting hyperplane is always below the epigraph. Actually, this is what we are using. Okay, and again we use contradiction. Got it? And here comes very interesting equality constraint function. This one, affine function, right? We've seen this in linear programming. And I never said that it's a convex set, but it's a convex set. Now, given that, yes, some of the problems have just this constraint. So you just need to prove your objective function is convex, then you have proved the problem is a convex problem. Got it? Now we talk about some general case where H is also differentiable. And what is this? This is the Lagrange condition. And we show that if this condition holds, then it's a global minimizer. We skip the proof. And now we move to the Kkt conditions. So we have equality and inequality constraint. Be careful. Sometimes equality constraint does not give us convex constraint set. And let me give you a very, very simple example. Because I've made a lot of mistakes. So suppose that you have this. What is this? This is a norm ball with two norms. So in two-dimensional case, it's a circle. Am I right? Without containing the inside and outside. Only the points on the circle. Am I right? And if you generalize, this becomes what? Hypersphere. It becomes a sphere in three-dimensional case, and it is called hypersphere in general n-dimensional Euclidean space. Now question. Here, let's say this function as an equality constraint function. By the way, let me ask you a question. Is this function a convex function? Yes. This is a convex function. Even this is a convex function. But if you set this to equal, what happens? You don't have a convex set. Be careful. I myself made a lot of mistakes by this simple, too simple, obvious set. No point is actually, no two distinct point is on line of sight. Right? You cannot see. So this is not convex. Okay. Not convex. Anyway, so let me go back. So when you talk about convex set, oh, by the way, be careful. This set may not be convex, but sometimes this intersection may make this entire set convex. So don't be so early frustrated. Okay. Another one is this. Even though you have this constraint, sometimes you may relax this constraint. Like what? Like this. In that case, since this norm square is a convex function, this is a sublevel set of a convex function, which means that this becomes convex. Now, you just see that sometimes that, you, by relaxing the constraint, you turned your non-convex problem to a convex problem. Got it? And you solve, and fortunately, equality holds. Got it? So never be frustrated. Relaxation, even though I didn't make enough emphasis, but relaxation of constraint is one of the best strategy in tackling, I'm not saying solving, in tackling an optimization problem. Okay? Sometimes by just relaxing, you see something new, entirely different thing, very simple. Okay? Another one is actually partitioning. Okay? So relaxation means that, okay, suppose this is Rn and you have omega. Relaxation means that you consider some omega prime, bigger than and containing omega. Another one is partitioning. What is a partitioning? Suppose you have this omega and you divide it in a clever way. And interestingly, sometimes in each sub-constraint set, the problem is convex. And you may see some in the final exam. Okay? I emphasize, don't never say that you never taught this technique. Partitioning is very important. Actually, I've told you some story in the midterm. Okay? So partitioning is very important. One of the ways to do partitioning is that, for example, you have some minimization of x and y, and you turn this to minimization over x and minimization over y, but be careful. Sometimes this and x, y, this problem may not be an unconstrained problem. It may be a constrained problem. In that case, you have to carefully choose the constraints here and there. Sometimes this constraint is dependent upon this variable. Okay? Anyway. So, yeah. Suppose this is a convex optimization problem. Of course, you may say that this is convex, but here we assume that this gives us a convex and this also gives a convex. In that case, what is this? The Kkt condition. This is complementary slackness and this is dual feasibility, right? So this is for convex optimization problem is necessary and sufficiency for global optimality. That's it actually. So I've quickly covered this lecture note, and it seems I have enough time to cover the next two notes. For this one, as I told you, I've updated, I myself have written it. Okay? Originally, I have selected some pages from Professor Boy's lecture note, where I talk about some convex cone, dual cone, and generalized inequality, but I just removed that part. Okay, and this is much simpler. So the title is Multi-Objective Optimization, and this chapter number is the chapter number of the 4th edition. This is newly added compared to the 1st edition. When I was taught using the 1st edition, there was no chapter like that. At that time, the entire course, entire textbook was dedicated to so-called the single objective optimization. Single objective optimization means that you have a single objective function. So single scalar valued, actually real valued objective function to be maximized or minimized. And you may say that this theory is complicated and lengthy enough. But in the meanwhile, the engineering problems where multiple competing objectives caught a lot of attention. And that's why the author included new chapter. And as an entry into single objective, people use multi-objective. Sometimes they call it multi-criterion. But actually, multi-criterion, multi-objective, the precise definition vary person by person. Okay? The Stephen Boy's textbook distinguishes multi-objective and multi-criterion optimization problems. Why this our textbook, the authors of the textbook just say that they are the same name. Multi-criterion optimization is same as multi-objective. But it varies. Okay, be careful. Now, the formal statement is this. Still, we consider a vector, a decision parameter x. But here I use the boldface f. What does that mean? This function is not a function into R. Now it's a function into R to the L. So how many functions do we have? L functions. Okay, where do I have? Okay, it seems I don't have it. Okay, so anyway, L functions. And now let me ask you a question. Okay, how do you define an optimal solution? If you have L greater than 2, for example, L equals 2, how can you define? So let me visualize. Suppose you have 2 points. Like this, in the Euclidean two-dimensional space. Which point is smaller than the other point? A and B, which one? Unlike one-dimensional case, where we have natural ordering, right? A is smaller, right? B is greater. If we just move to one higher dimensional space, there is no natural ordering. We have to set up our new definition to say that, for example, according to my new definition, A is smaller than B. Okay. Why I say this? Suppose you have objective function looks like this. In that case, this point may correspond to f of xa, and this point may correspond to f of xb, where xa and xb are feasible to our multi-criterion optimization. Be careful. This is function value. Okay? Got it? We need some way to compare. So the simplest way is what? The simplest way is to use this property. Okay. Consider. Let me give you a motivating example. Suppose you want to minimize, okay? You want to minimize length to vector. And suppose you have 4 points like this, okay? This is f of xc, f of xd, this is f of xa, this is f of xb, okay? So I just copied these two here. Got it? But introduce 2 more points. This is for f1 axis and this is for f2 axis. Now I assume that the f2 values of these 2 points are the same. Now, what do you want to claim according to your intuition? f2 is the same. Then you want to say that f of xc is smaller than f of xa, right? And also, what you want to say is that f of xc is smaller than f of xb because they have same f1 value. Now, what about these two? f1 value is worse here. f2 value is also worse here. So, given these 4 points, rectangle is given 4 points. How many comparisons can you make for choose 2? So you have 6 combinations, am I right? If you compare this one, you can say which one is smaller. If you compare these two, you can say which one is smaller. If you compare these two, you can say which one is smaller, which one is smaller, which one is smaller. So among 6 combinations, only one case where you compare these two is just omitted. Okay, we just do not say anything. It seems okay. And this is the idea of Pareto optimality. So what we do is this one. In 2-dimensional case, it's like this. Let's say that this Rn plus. Okay, this is defined as x in Rn, where all xi is greater than or equal to 0. So what is this? First authent. Got it? Now let's define some strange operation like this. So you add x0. And what is that? Simple. This is a set of points in Rn such that x minus x0 is in Rn plus. Got it? So you just move the origin. For example, here, given this point, what you do is that you move this first authent to here. And every point in this moved authent is what? Is no better than this. Right? Same. You move this to here. Since this point is contained in this moved authent, this is what? No better than this one. Same thing. But what about these two? This is out of this area and this is out of this area. Actually, if you extend this idea, I just mentioned convex cone. Okay? Cone means you have some circular thing, but anyway, this may be assumed as a cone. So that's why the people have that idea of using a convex cone to introduce a new inequality definition. But anyway, forget about that. And what we have is this. Okay. So suppose that x star is a Pareto minimizer or Pareto minimizer. Pareto, this is standard pronunciation. Pareto minimizer. If no x, okay, so here x satisfies this. Actually, it means that no x dominates x star. Dominates means that better, at least in one objective. Got it? So here, what? For this one is dominated by this point. When we compare F2 value, am I right? This one is dominated by that point in F1 value. This point is dominated by this point by in X1 and X2 value. However, when you compare these two, right? Is this point dominated by that one? No. Is this point dominated by that one? No. Dominated means that every objective is not better. Okay? But here, this says better F2, but worse F1. This says compared to that one, better F1, but worse F2. Got it? So, the idea is like this. Suppose you want to minimize two-dimensional function, and you find some points, Pareto minimizers. So say that E, F, G, H are Pareto minimizers of your two-dimensional multi-criterion problem, then what must happen? Suppose this is f of xe. Then you moved first orthant. No other point must be inside that cone, right? So the other points may be in other place. However, this should not be dominated by anyone. So only possibility looks like that. So something like that. Okay? Got it? Now, in this case, we have finite number of points. Suppose we have uncountably infinite points. In that case, we may have some lines like this. See that? At any point, if you move the first orthant, so you move the origin to here, no other point is inside here. Got it? So Pareto, this is called the Pareto front. Always looks like this. Okay. By the way, why this is so important? Because actually this is the way we live in political world. For example, suppose this one f of xe, suppose xe and xf are two possible public policies that can be adopted by a new government, for example, new Korean government. And if you choose, for example, policy xe, what happens? For example, it's good for me, but bad for you. Okay? Good for professors and bad for students. And if you choose that policy, then it may be bad for professors and may be good for students. Which one is better? Right? But this is the problem of politics and public policy. And also, this is what happens in every debate TV program on Wednesday night, 백분 토론. Okay? And in many cases, actually what they say is interesting. This is one of the panel claims. That is the point, the other panel claims. So actually, whenever I watch, I want to say this. Hey, panel A, there exists this point. Okay, this is better than that one, right? And also what? Better than this one. But they fight each other, saying that this is the way, and no, that is the way. Okay, so. And they say that this one is unique according to their point of view. Okay, unique way to fulfill justice or something like that. I really hate it. But anyway, so this idea of understanding what is a multi-criterion objective is very, very important for you to live this crazy world, because people actually fight each other. Because world is like this. Okay? So whenever you really want to become a negotiator, try to find some point like that when people fight each other with these 2 points. Then you satisfy everybody. However, unfortunately, in many cases, two opposing parties supporting the policy that results this objective function vector and that objective function vector. So For example, some of the people must be sacrificed, professors or students, for example. Got it? So then which one is justice? There is no justice as far as they lie on the Pareto front. Okay? There is no justice. However, if there is small offset, then there is better policy. Okay? But sometimes nobody knows. So here, what can you say? If some people just support his own opinion very vigorously, you may say, okay, it's your opinion. Right? According to your criteria, it's better. So just don't fight. Okay? People have different value system. People have a different value system. So according to their value system, which may scholarize, I'm going to say, okay, this achieves the lower objective than that one. Or some people say that this achieves lower objective than that one. But life is not that simple. Okay, anyway, so I explained the Pareto front and Pareto minimizer. And computing the Pareto front, that is the section 3 of the textbook. Just read it. This is important, okay? Because you will see in the next semester, if you take the 645, the statistical signal processing, there will be a lot of optimization problems in statistical inference. And many have competing criteria. For example, in your radar system or in your test kit for hepatitis or something, what do you want to see? You want to see type 1 error and type 2 error both very small. And you will learn what is type 1 and what is type 2. But anyway, there are two types of errors. The problem is that if you want to decrease type 1 error, usually type 2 error increases. So you have to have some trade-off. So actually, naturally, such problem is a multi-criterion optimization. However, it's difficult to solve. So what they do is that they convert multi-criterion problem to a single criterion problem. And there are 4 popular ways. I'm not saying that these 4 are the only ways. There are 4 popular ways to convert. And first one is to use this one. Suppose this is an original vector objective function. You introduce a weight and sum. So this is what I just told you, right? In the previous page. There are 2 points. And one people have this weight, so this is your level set. And saying that, okay, this policy is better than that one. When we minimize something. But this person has different point of view, value system. Got it? So anyway, you introduce some proper weighting vector, and then you scholarize and solve. Another one is minimax. This is minimax robustness. Okay? So see that, suppose you minimize maximum of that one. What will happen? Worst case is suppressed. Okay? But you know that that is not a good policy. For example, around 2 months ago, there was some threat felt from North Korea. So what did I do? I went to Lotte Mart and purchased the cereals. What happens? Well, cereals may go over the effective date in a year, right? So if you want to behave very robustly or very safely during putting a lot of margin, then the problem is that the minimum also may not be that small, right? But this is a very robust way. If you do robust control and if you do some robust something, you always see minimax. When original problem was minimization problem. Okay? Another one is that. So you use norm. Okay? So square sum, or you calculate the cubic metric and sum, something like that. Okay? Another one is this one. This one is very, very popular. So you choose, for example, the first objective function as the objective function of the single optimization problem, and then you put upper bounds on the other constraints. Okay? Actually, this is a lot adopted in statistical signal processing and other cases. And also, actually, you can find some relation between this problem and the Pareto optimal front, the problem of finding Pareto optimal point. Also, this one too. Okay, very interesting. Anyway, so I listed here some problems like this. In statistical signal processing course 645, you see receiver operating characteristic of radar system. Then you have two competing probability of errors, probability of miss and probability of false alarm. And then you have receiver operating characteristic. That is the Pareto front. Okay. Second method, you can find the minimax criterion in hypothesis testing. Okay, binary hypothesis testing. You will see in 645. Okay, and interesting, you have an equalizer rule, and it's very interesting. And fourth one is what? You put one of the function in the objective and all the others in the constraint with some upper bound. Okay, that is related to alpha level Neyman-Pearson hypothesis testing, and you will see. Okay, probably in September, immediately after the beginning of the course. Also, some related detectors are uniformly most powerful detector, and this is a little bit different, but anyway, uniformly minimum variable unbiased estimator, something like that. And also, in information theory, you see multi-criterion problems. For example, suppose you want to compress the output of a source. Then what are the competing performance metrics? One, compression rate. You want to compress a lot. The problem is that if you compress too much, you will distort the recovered signal. So amount of distortion and this compression rate are competing performance metrics. In that case, what do? Interestingly, if you take the information theory, you will see something similar to Pareto front. So you will see something like that. And this is amount of distortion. This is the compression rate. Okay. So you see the Pareto front. Okay. This point is not dominated by that point. Got it? And also in single-user communications, you have here bit energy per noise density and bit error rate. And if you choose different spectral efficiencies, then you have different trade-off curves. Here, you want to transmit very fast. In that case, given the same bit energy per noise density, your error rate is very high. By the way, this is low scale. Okay, something like that. So actually, everywhere you have multi-objective optimization problem. In multi-user problem, this is more vivid. For example, you have two users. Okay, so transmitter 1 and transmitter 2 competes each other over the channel, wireless channel. So they want to occupy more resource. Now, transmission rate of TX1, that is R1, and transmission rate of user 2, that is R2, competes each other. They want to maximize their own. And interestingly, according to information theory, in many cases, it looks like that. This is a Pareto front end. In this case, we have maximization. And by the way, this area is capacity reason. Something like this. Okay, so you will see a lot related to this. Yeah. Now, let me move to the last one. So it seems I'm over time, but this is very fast and does not take much. We have chapter 19 of the fourth edition that is dedicated to integer linear programming. That is slightly different from our linear programming problem like this. See that? Constraint, the objective is the same. Constraints are all okay, but not here. So the component of x vector can only be integers, positive or negative, 0. Okay. How can we solve this? Usually, this problem is a combinatorial problem with very exponential complexity if the feasible set is very large. But there is a small subclass of integer linear programming, and that is kind of just provided in this textbook. So they introduced the notion of unimodular matrix. Unimodular matrix is related to this matrix A, usually fat matrix in linear programming. And now what you do is that you have a bad matrix. And what you do is that you select, you choose columns so that you have a square matrix. Every square matrix has its determinant 1 or minus 1. If that is satisfied, that fat matrix is called unimodular. And interestingly, in that case, your simplex algorithm just gives you the solution. So you just solve the problem as if it is not an integer linear program. It's just a linear program. But this is a sufficient condition. Some problems, some integer linear program problems can be solved in a different way, even though that matrix A is not unimodular. But yeah, we do not use much. Now, the last one is variational problems. What is a variational problems? This is quite interesting in that our decision parameter is no longer a vector, it's a function. So it's like this. Let me give you an example. The first one, Brachistochrone problem by John Bernoulli. And the idea is like this. So here, the height is, let me use y0, and this length is x1. Now, you want to build a slope so that frictionless bead moves on that slope. It reaches this point in the minimum time. What is your intuition? So here, you want to find some function that satisfies these two conditions, right? At 0, function value is y0. At x1, the function value is 0. And you want to find the continuous function. Continuous function. So that if you put a bead here, then this is the direction of gravity, so it moves and reaches here after minimum time. What is your intuition? Anyway, the problem is different in that your objective, your decision parameter is a function, right? And your objective function is the minimum time elapsed depending on this function. Such objective function is called functional. Okay? Of course, functional means a bigger name, but anyway, you may say that a function or function. That is functional. So you want to minimize a functional by finding a function. And you may say that, well, let me just sample this very finely, then it becomes a high dimensional descriptor. Well, of course, you can approach like that. Okay? But anyway, those mathematicians in 17th and 18th century wanted to solve this problem exactly. And what do you guess? Straight line? No, actually it's a cycloid. Amazingly. Anyway, another one, this is by John Bernoulli's Brachistochrone problem, and the other one is this one. So when Newton challenged by this problem, he solved it in one night by inventing calculus of variation, and also solved this problem later. The idea is this. This is Earth. And let's say this is Tripoli and this is Seoul. Okay? and you want to dig a hole, tunnel, and you want to put a train here, and that train has no friction, air or surface, and it only uses gravity to reach here. What is the tunnel shape that gives you the minimum time elapsed? So do you see the similarity and difference? Okay, here the gravity field is constant, but here it depends on the location, right? As you know that if it is here, only the material inside the sphere affects the gravity, but outside does not, blah, 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 as you learned in Gauss' theorem in the physics 1. So, and this is something like this. You put a circle here, and you roll it, and then it's called hypocycloid. Newton proved it. I do not know how to derive. Okay? Another one is something like that. Here, around the BC 850, Queen Dino of Carthage is, as we last time discussed, Carthago, right? You know that Roman and Carthagos were Hannibal and what was Roman Empire's general? Anyway, do you know the story, right? So Queen Dido was given a present. It's like another king said that, okay, here is your present. What you do is that, given a herd, so simply speaking, a string of a finite length, you take land that can be enclosed by the string. And this is her policy, to draw a circle or something like that. Okay, I'm not sure. Okay, anyway. So, yeah, there are many examples, but important thing to electrical engineers is this one, optimal control. So actually, in our department, they teach these variational problems in control area. But I'm not going to talk about that. If you want to learn, take optimal control course in our graduate curriculum. Anyway, the idea is very simple. We use almost the same idea as we did. So we cannot solve every variational problem. By the way, if we want to find a function that optimizes some function, that is called variational problem, because we define so-called Gato variation. That is differentiation of functional with respect to feasible direction. That is a function. Got it? So it's kind of, they use this first order necessary condition type thing. And interestingly, the idea is like this. If this is function, okay? This is not a vector. If a function is an interior point and local minimizer, then this Gato variation is 0 for all possible functions. Okay? So it's like first order necessary condition. Gradient is 0. Now we have surprisingly Euler-Lagrange multiplier theorem. And here the difference is that objective functional's Gato variation is linear combination of the Gato variation of the equality constraint function nulls. And here, John multiplier theorem corresponds to the Kkt condition when we don't have equality constraint functions. So again, here we have Lagrange multiplier that is greater than or equal to 0, and we say that the complementary Slagness holds surprisingly the same, right? And we have what? Gato variation of the objective functional is the linear combination of the Gato variation of inequality constraint functionals. Got it? And okay, of course we can combine that and we have something similar to Kkt conditions. Of course, first order conditions may not allow to find the candidate functions. But fortunately, those problems I've given you, Brachistochrone and Brachistochrone through Earth, Queen Dido's, those problems that can be solved using only this one. And if you want to enjoy some solutions, ask me. I have a good textbook. Okay. Anyway, so this is all for the lectures. And let me just quickly summarize and finish this course. So we've worked very hard to cover the entire textbook, actually. Probably you've never done that in a graduate course. But anyway, in first part, we did mathematical review, mostly on multivariate calculus and linear algebra, especially in the Taylor series approximation. First order, second order were very important in multivariate calculus. And then we derived some first order necessary conditions, second order necessary conditions, and second order sufficient condition for general unconstrained problem and some constrained problems. And then we moved to line search, where it is one-dimensional search that is very important in any numerical search problem. And then we moved to algorithms, gradient methods, Newton's method of secant, conjugate direction methods, you still remember? Yeah. And their variations. And some least square problems. And also we studied neural networks. And you've seen that actually many AI, artificial intelligence area is just one, a simple application of optimizations. So you can expand your knowledge to this area. And also we considered linear programming, because this is a very good example of convex optimization problem. And then we studied general Lagrangian and duality. And then we came back to linear programming and tested our knowledge earned here. And then we learned Lagrange multiplier theorem, and we learned Kkt theorem. And then finally, in convex optimization, we've seen that these first order necessary conditions actually gives us global minimizers. And we covered some miscellaneous. And as I told you, this is entire course. And this is a one semester single course. So you have a lot to study, but this course is designed to give you, expose you to some principles of optimization, so that when you take, especially the 645, you have better understanding. Okay? So I believe some of you will meet me again in next semester in 645, and you'll find that this course helps you a lot. Okay? Anyway, exam is on next Wednesday, and probably my TA and I will give you some pointers, some hints for the exam, because the coverage is too wide and you can easily get lost. Okay, but study very hard. Don't wait our emails. Okay, study first and then wait. Got it? Okay, that's all for the day. That's all for the semester.